Thank you all for attending this second edition of the Pulse X-ray series that we're running from Nordson Dage. I'll pass you over to the UK. We have our application specialist. Sandeep's actually going to focus on one particular area of capability with the Dage X-ray technology, looking at 3D X-plane CT. So without any further ado, let me pass you over to Sandeep.
Yeah, firstly, I'd like to thank everyone for joining today also. And as Steve said, today's session is going to be, the title is the Advanced X-plane CT User. And what I want to focus on today is showing you the advanced capabilities that X-plane has. But also I'm very excited to introduce some new developments of X-plane today. So the three key areas I'm going to focus on is how to acquire good results now in less than 1 minute. So this is a new development. When best to use low and high scanning angles. So this seems to be a confusion that our customers come to us with quite a lot. So I want to try and clarify when best to use these today. And I want to give more information about how to improve the X-plane images so that you're getting a better model, and then also cover a little bit about the visualization software, which is going to be focused around volume graphics today. So I'd like to begin with showing you our new developments, and these new developments include a super fast X-plane scan. So like I said, less than 1 minute. Now, X-plane scans have always been fast. Generally you could get results, good results in about 2 to 3 minutes before. But now, using these new settings, if I move to my area of interest, they're even faster. Now, if I want to run an X-plane scan on this QFN device here, you can see to the left of this QFN, there's a little ball that's been placed. Now, this ball is generally used for remote fiducial scans. But because today I want to focus on the advanced features, for someone who's at the advanced level of X-plane, should be able to do a local fiducial scan on this QFN. So that's what I want to show you today. So I'm going to start by zooming in. And when you're using a local fiducial, what you're looking to identify is a feature which is circular, not going to be obstructed much, and can be used as a local fiducial. So I've identified this void over here as my potential fiducial point. So what I'm going to do to begin with is set the height on this. And because all I'm interested in achieving here is separating the layers so that I can work out where these voids are, in which layer, and also trying to understand how many layers this QFN has. So because that's my aim, I'm going to use a low angle. So when I say low angle, I'm going to do 20 degrees. And what I'm checking here as the machine moves to 20-degree angle is, has my crosshair, the center of the crosshair, remained on the fiducial that I want to, or on the void that I want to use as a fiducial? So it's slightly, quite high up. I want to bring it towards the center. I'm just going to adjust this height value. Okay, and as I'm doing that, can you see that the center of the cross is now more toward the center of that void? I'm going to do a quick orbit, just checking that the cross crosshairs remain on that void. If the crosshairs start to drift off the void, then I need to adjust the height value. But in this case, it looks good. I'm going to stop the orbit, return back to 0 degrees. Okay. And then just bring the whole QFN back into the field of view. So the image you see on screen at the moment is a raw X-ray image with a little bit of filtering. So I'm going to turn that off. And I'm going to apply a static filter, in this case, deep contrast. So this deep contrast filter is available in all Genesis software versions now, especially on the latest version. And what we have in this filter is 3 different types of enhancement. So the ALC filter is improving contrast. The median is reducing noise in the image, and the special is applying some sharpening. So if I turn this filter on, you can see that massive improvements have been made to the image. So it's very important before you run that X-plane scan, you apply a good filter. Because every image we take, it will be improved with this filter, meaning that the end model will be really good. Then I'm going to go to the X-plane tab. So I'm going to select 20 degree in this menu. And in the new version of Genesis software that will be released into the field very soon, you will see 2 new options in the number of projections menu, okay? And these 2 new options will be 9 and 18. And these 2 new options will allow you to achieve these super fast X-plane scans. So today, what I want to show you first is a 9 projection scan. Click Start. Next, I'm going to draw a box around the fiducial point. Now note how I'm drawing this box. Okay, so I've drawn it big enough so that I'm capturing the contrast of the void, but also the darker contrast of the solder paste behind. Having a box of this sort of size and capturing those different contrast levels will allow the software to detect that point a lot better. Click Start. Okay. Now keep an eye, I don't know how well you'll see on the screen sharing here, on how fast this scan is. Okay. So the total time for this scan is around 40 seconds. That's incredibly fast, and will make our X-plane scans even more competitive in the field and against other systems. Far superior, I believe. Okay, reconstruction taking place now. So when you come to look at your results, apply a sharpening filter. I tend to apply this real local contrast. It's a very nice filter. Adjust this filter strength to what you require. And as you can see, in about 40 seconds, we've got some good results here. Okay, we can see the different layers. So this is the top of the QFN. You can see the wire bonding. As I scroll through, okay, we see 1 layer of solder paste, see some voiding. See another layer of solder paste. We see the pads, some bridging. Okay, it's a bridge around the edges here. See the voids in the pads clearly. Oh, sorry, wrong way, other way. You see some larger voids in a layer of solder paste here. and then the PCB. Okay. So you may be thinking, well, what's the point of this scan? Because the results are not amazing. Yes, to achieve the amazing results, you need to do the longer scans, but in 40 seconds, those results are very good. And the point of this is to really now allow our customers to do these super fast scans to just quickly understand how many layers they are in the PCB, how many layers there are to a component, and to just very quickly do voiding analysis. We've had many requests from our customers, that they're not interested in achieving the best results all the time. All they want to do is just a very quick separation of layers to understand the device better, or to very quickly do a voiding analysis. So that's why we've brought this in. Okay. Next, what I'm going to show you is when best to use the high angles and how to set these up. So if I move to a BGA device, we'll look at the corner of this device here. So the key differences between a high angle X-plane scan and a low angle X-plane scan is really what you're looking to achieve. What is it that you're interested in? Because if all you're interested in is separating the layers and doing a voiding analysis, then the low angle is ideal, because you're only interested in the Z plane. If you're interested in looking for opens, non-wets, head-in pillows, then the high angles are ideal. So what I'm setting my next scan up to do is check for head-in pillows and open connections on this BGA. So I'm going to focus on this grid of 9 balls here, 3 by 3. The first thing I'm going to do is set the height. So to help you set the height, you could apply these live filtering and live contrast stretch for a better image. Just going to place the crosshairs in the center of the ball. And set the height. When you're looking for head-in pillows, opens, you need to be looking at the X and Y plane. So when I refer to high angles, what I'm talking about is anything that is 45 degrees up to 60 degrees, which is the maximum X-plane will go up to. So this scan today, I'm going to do a 50-degree scan. So the first thing I'm going to do is just check the height setup. So manually type in 50 degrees and do an orbit, and just check how well the center of the crosshairs stays on the ball that I've just calibrated the height for. Okay. So it's fairly steady in the center of that ball. There's very little movement, which is indicating that the height has been set well. So I'm going to just return back to 0 degrees. Okay. And go to the X-plane tab. Bring back my right-hand panel. I'm going to turn off the live enhancements because that was I only needed that for setting the height. And I want to apply my deep contrast filter again. This time, like I said, we're going to do a 50-degree scan, so select that in the menu. And we'll do an 18 projection scan this time. So still super fast, but not as fast as the 9 projection. Okay, click start. Again, make note of how I'm drawing this box. Drawing a fiducial box like this is not good, because what you've got is very minimal contrast for the software to go on for identifying that point. So what you want is some dark contrast and some light contrast. Just position the box something like that, and then click start. So the total time for this scan is about 1 minute and 30 seconds. And we're collecting an image, one image every 20 degrees. And the machine will complete one 360-degree orbit, collecting 18 images. And every time the machine moves, it stops. It then averages the image, and then you see this little flash on the screen. This little flash is the filter being applied. So again, reiterating the point of every one of those 18 images being enhanced with a good filter means that the end model looks nice. Okay, just going to reset the contrast here. Now we'll have a look at this data very quickly in the Z view, but that's not the area of interest for this scan. I want to just very quickly have a look. Okay, you see the voids, improve contrast. See PCB information. Okay. We can see that there's a problem with these solder joints. So let's have a look at the Y view and what it looks like there. Okay, so these connections look fine. We can see position of voids quite nicely. See a void quite high up in this solder joint. Some interfacial voids. Okay. Continue to go further, and you see, very clearly a joint here on the right that looks different to the ones to the left. This is a typical head-in pillow, and that's what a head-in pillow would look like in X-plane. If you wanted to then check which solder joint this is, if you move back to the Z view, you can see that these two here are the good ones, and this one to the right here is the bad one, or the head-in pillow. And let's go back the other way. Okay. We're seeing again this extra bit of material on this solder joint. And you can see that these two are separate. It looks different to the two on the left. Again, indicating head-in pillow. That shot there shows it very clearly. Let's have a look at the X view. Head-in pillow, another head-in pillow here, and the head-in pillow there. So that's how I would recommend setting up a high angle scan. The precision is in setting up the height very accurately, applying a good filter, and choosing the right angle. Again, a 90-second scan, and results are good. Good enough to be able to analyze for defects. If I return back to the inspect mode, next we're going to look at when best to use the low angle and the typical application for the low angle X-plane scan. So if I go to my map, I go to this PCB over here. Many of you may see applications like this on a daily basis where the PCB is highly populated. There's components on both sides of the PCB, and also this BGA has a metal shield over it, so it's quite a dense area. This is a good area or an ideal application of where the low angle really shines. Let me show you why. If I zoom into a solder joint here, what I'm going to do is just turn off this filter for now and use my live filters. If I wanted to do a high angle scan here, so for example, this ball in the center of the cross, I'm thinking about using as a fiducial. Now I go to 50 degrees. Okay. Do an orbit. You'll see that there's many things that will come into its way from below on the other side of the PCB, and also the different layers within the PCB are all the contrast from those layers is all causing it very difficult to track one precise position. But it becomes a lot easier when you use a lower angle. Okay, so what I'm going to do is first go back to 0 degrees, just set the height on this board. And then I'm going to set up a 20-degree X-plane scan. Let's see how well that's been set. Just going to adjust it ever so slightly to bring the cross more toward the center of the ball. There we go. And do my orbit. Now during this orbit, you'll notice there's a lot less features getting in the way of that ball I'm trying to track, which means that the software will be able to detect it and track it a lot better as well. Okay, so I'm happy with that. I'm going to stop the orbit, return to 0 degrees. I'm going to zoom out to bring my region of interest back into the field of view. In this case, my region of interest is this complete center area here. And I'm interested in separating the layers, just understanding all of the different layers that are in play here, because there's quite a few. I'm gonna bring back my right hand panel, turn off the live enhancements, and turn on my deep contrast filter again. Return to the X-plane tab, select 20 degrees, and we'll do a fairly quick scan again of just 18 projections. This time what I'm going to do is adjust the Z step to 3. When you put in a value into this box, what the software does is calculate the depth of the 3D volume that will be reconstructed, and that can be seen here. The depth will be 2.50 millimeters. And this calculation is based on the value that you input into this Z step, the field of view that you're using. Just so you know, the maximum Z step that you can have is 10. Okay, I'm going to now start my scan. Draw a box around one of these solder balls and click start. Again, the setup that we're using here is advanced level. If you've got an operator who's at a beginner level for X-plane, they may feel more confident to do a remote fiducial scan here, where there's no chance of the fiducial point being lost. Once you've gained more experience and more confident with using this tool, you'll be able to set up these local fiducial scans better. Okay, reconstruction taking place now. Again, a very quick scan with some good results. So let's have a look at all the layers we see. Right, so this is the top of the device here. We've got many of these micro bumps. Note that the contrast is not that great. Again, you've got to put that down to it being a quick scan. So if you require higher resolution, then you need to do a longer scan. And I'll show you the difference next. Okay, so top of the device, then coming down, see the solder balls, see some voiding, quite small voiding, nothing too concerning. PCB, and then we start to see all these components that were obstructing our BGA device on the other side of the PCB. Okay. So like I was saying, if you require higher resolution results, then you need to do a longer scan. And I have something prepared for you today just to show you the difference. So what I'm going to do is load in the slices from my longer scan. Okay. So this is the data from a 20-minute scan. Note that the contrast on the bumps is better. There's a better edge detection around each bump as well. These bumps are very small. Okay. Solder balls. Note how much more clearly we see these little voids in the solder ball here. Yeah, particularly there at this slice, we're seeing a lot more detail. Okay. PCB. And then our components on the other side. Again, look how clearly we see those solder voids now. And the contrast is improved. So this is what you get with running the longer scan. Okay, next what I want to show you is a little bit about the visualization. So as you may all know, once you've acquired this X-plane data, you can export it out of the X-ray machine and send it to a 3D viewer that we offer. So we offer two packages. We offer one which is called Sarah and one which is called Volume Graphics. And I'm going to show you Volume Graphics today. So this is data of a BGA that I'd acquired previously, and I just want to show you the process of how to visualize nicely. So the first thing you want to do once you've got the data into the software is improve the contrast of the slices. So that's what I'm going to do first. You can see as I'm doing this, you can adjust the contrast for your own liking. So I'm going to go with a dark contrast and something like that. If I move to the slices, a key difference between looking at the data in this viewer and the X-ray machine is that we're seeing the X, Y, and Z view at the same time. On the X-ray machine, you see what you see in the X or Y or Z view. Okay, we can see some voids in the solder joints. Okay, note here on this solder joint here, we see a little crack. I'm going to zoom in to this crack. Okay. And one nice thing about this software is if you want to quickly identify where this feature of interest is in all of the views, you can apply what's called an indicator. Okay, and that will then point at the same feature in all the different windows. Okay. And also the 3D view here. Now what's quite nice about this software is for visualization, you can really go crazy. And one way to go crazy is you can highlight a single ball in a different color and separate it from all the others. To highlight that this one single ball is showing a feature that the others are not. If you want to quickly see this crack in the 3D model, and apply these, hit the scissor button. That then crops the model in the exact slice of where that feature is. And you can then zoom in and take a look at that feature from any angle that you like. Trying to bring you in closer here. Oh, there we go. Yeah. I'll zoom in, and you can see exactly where the crack propagates from to the point of where about it isn't. Is it going right the way across the ball or just partly through the ball? In this case, just partly through. Another nice feature about this software is the ability to do porosity analysis. So that's what I want to show you next. I'm going to just turn off this region of interest, zoom back out and have a look at these voids. So I'm going to find a layer where there's quite a few voids and then start the process of the analysis. Okay, let's stop here. Zoom in a little bit. Okay, there. I want to define a region of interest, so I'm going to draw a rectangle around an area. Okay, and also define it in one other direction. Okay. Just bring my slice position back. Okay. Now I'm going to save this. And before you can do a analysis, you need to do a surface determination. So once you've highlighted the region of interest, you can define a surface. And what you need to do next is adjust the threshold lines so that we're not picking up all this excess background noise. I'm going to pull this line across. And as I'm doing that, you can see we're picking up less noise and it's becoming cleaner. And I'm going to stop about there. Okay, that looks good to me. Click finish. And we can move to our porosity analysis. Right click, create. Oh, bear with me, wrong one. Create. Okay, this one. And okay, the settings I would use is to go to relative, turn off filter result, make sure you have preview selected, and then in the bottom right corner here there's a bar which is just loading, so be patient. Okay. And then what the software has detected here is where it thinks the void should be. And you can see that it's picked up a lot of background information, which is not right. So I just need to adjust the contrast here. I'm going to change that to a different value. And it's just working out the new numbers. And you can see it looks much cleaner and tidier. So I'm going to accept that and calculate. This takes a few seconds. the difference in terms of what we're doing in this software compared to what we do in the X-ray machine is when we're measuring voids in the X-ray machine, we're measuring voids in X-plane per slice and not a volume measurement. What we're going to be doing here is measuring voids in the total volume. Okay. Change the settings. And now you can see that there's a color code to the left here. And all of the voids are now color coded per volume information. And you can also see these voids in the 3D model. I get rid of it, bring the whole model back. What I'm going to do is make these solder balls transparent. And what we're seeing here is a blue and purple voids, and you can change these colors. So the voids, according to the key color map here, are quite small, and you can see the purple right down the bottom and the blue towards the bottom, but just above the purple, and that's what we're seeing here. And what I'd like to do, just to finish off, is just bring all of the information I've given you today, from acquiring the data to visualization and presenting it to you in a video to show you the capabilities of what can be. So I'm going to just finish off by playing this video, and then we can take any questions. So you can see there's different volumes being applied here. There's one volume showing the PCB, and then the second volume we're showing the solder balls, and we're bringing the information through slice by slice. Okay. The visualization has now been adjusted to make the solder balls transparent, and now we can clearly see the exact location of these voids, whether they're at the bottom of the ball, the middle, or the top. And we're seeing a lot of interfacial voids on this data. Okay, this here is showing segmentation, where one ball is separated from the others to show off a certain feature. And you can move the camera in different views to look at the feature from different angles. And you can make very nice videos to present to your customers once you've done the analysis work. Okay, well, I hope you all enjoyed today's session. That is the end of it, and I really appreciate you all joining again and for listening. Over to you, Steve.
Yeah, thank you, Sandeep. Excellent. It was a very good account of the X-plane technology. I hope you all enjoyed it. I didn't get many questions, guys. I was eagerly awaiting questions. I think the only one I got was Charles Go from Crest in Thailand telling me that he changed his name. But yeah, just to go over this, X-plane is just one component, typically or option, I should say, for the X-ray system that is supplied with the system as new, or we can actually upgrade the system depending on the age of the original system, and it comes with it in its basic format with just that slicing capability that you saw Sandeep explain at the very beginning. And then, of course, we have the 3D CT visualization. We're having two options. One is Sera from Siemens and VG that you saw Sandeep particularly use today. So there's different attributes for that software. And if you need more information about this, any of the distributors that we have in your territory will be able to provide that detail. The other thing to consider is we will be giving you this video, by the way, on your application. So if you want that, send either me or your local distributor or local Nordson engineer a request for this video. But also you'll find other videos that have already been published, including X-Plane, CT and other technologies that we have that you can find typically either on our own website or in things like YouTube. So Sandeep particularly is one of our stars, our main star, of course, and I'd like to thank him. But is there no other questions from anyone? Oh, Sirapur. Can it be adapted to existing machine? Well, I think I just answered that, Sirapur from Thailand. Yes, it can, depending on the system type. So the precursor to the current range, the Quadra series, which you now have a Quadra 5, but you also have some Ruby systems, and I would believe that in most of those cases you can actually upgrade the X-Plane capability, including the visualization, to some of that older XD 7600. Is that correct, Sandy?
Yeah, that's correct. You know, the great thing about X-Plane is it is retrofittable, and there's no additional hardware needed. So, you know, the price is very reasonable for what you're getting, and it's a fairly quick upgrade.
Okay, so another question there, Sandeep, is from Sanjeev, on the question on the Quadra 7. So looking at aluminium wires, which is always a task, can we answer that, or can you answer that for me? It does depend, of course, on the actual sample, but what would your advice be on a 1 mil aluminium wire?
Yeah, with aluminium wires, you know, they're quite challenging to detect using X-ray, but we have some very powerful tools available in the software to be able to help you. One feature I would recommend for detecting aluminium wires is the HDR image enhancement tool. This is a fairly new tool that we brought out not too long ago, and it works by acquiring images at different exposure times. So we can acquire dark images and bright images and then bring them all together, and that really helps in detecting aluminium wires. But also, when you're detecting low density material like aluminium, we would also recommend using either the carbon fiber tray or a mylar tray, because the standard inspection tray you get with Quadras is a aluminium tray, and if you're trying to see aluminium through an aluminium tray, that becomes even more difficult.
Yeah, and just to quantify that, at least you have the right system. Quadra 7, if any system can see that type of requirement, then the Quadra 7 is going to be the right system.
Yeah.
Okay, just one other one there from YW Ding. Can the 3D feature be used to analyze on a wire bond ball and stitch with the same resolution as shown in the video? So again, Sandeep picked on one particular application as a demonstration. Yes, we can look at wire bonds. Again, it depends on the application and the particularly the sample. There's broadcast published videos again that I think you'll find that might prove that. But let me try and find some particular examples of that YW. Sandeep?
Yeah. Wire bonding is it's an application that can definitely be inspected using X-plane. We are able to check the bond connection for the ball and also the stitch. The perfect solution for inspecting wires is probably the micro CT tool, but it's definitely possible with X-plane as well. It's just the micro CT gets you nicer results. But yeah, we definitely have application examples that we can provide you with if you're interested to show you the capability levels.
Yeah, one thing to consider with that is it does depend on the sample, as I said. If your sample is small, like a semiconductor package, then it's ideal for CT, where we can get very good resolution from a rotation effect on the sample, 360 degrees of rotation. So as Sandeep said, that probably will give you better results than X-plane. But of course, if your sample is very large and you can't rotate that sample around without the potential for collision, then X-plane is probably going to obviously be the only application to, the only technology to help you in that case.
Yeah.
Okay, so I think that's a good selection. Again, I'd like to thank everyone. We had extraordinary large numbers, 66 in total. We've never had that type of audience before. So I'd like to thank everyone for attending, and particularly the people that sent out the invites, the distributors, the agents that helped us on this. As I said, this event has been recorded, so if you'd like that, please make a request. And any other questions, come back to us. Thank you very much, and thank you, Sandy.
Thank you, Steve. Thank you, everyone. Bye.